Sir, your voice is not audible, sir. So you can present now, sir.
Madam, my screen is visible. Am I audible, madam?
Yes, sir.
Okay. Thank you. Sorry for the inconvenience. Some issue was there with the system. I'll proceed, madam. So good morning to one and all. First of all, I would like to extend my thanks to the Civil Department, KL University, especially the HOD Paul Raji Garu and coordinators JD Chaitanya Kumar and Dr. Lingeshwaran. And JD Chaitanya Kumar happens to be our student, Gayatri Vidya Parishad, earlier, maybe 10, 12 years back. Am I audible, madam?
Yes, sir.
Okay, right. So, good morning to all the participants, both the people from academia and industry persons. I would like to start my presentation. Thank you for your kind patience. So, my topic here is assessment of sustainability parameters in concrete systems. Actually, before I start my presentation, I would like to acknowledge and give due regards to Dr. Ravindra Gettu, Professor, Department of Civil Engineering, IIT Madras. I have taken the inspiration from his PPT. Some of the PPT I am using there, the same thing. I will just go through this. So first of all, I think we have been hearing this term sustainability from many years. Actually, sustainability in general, before you go for a specific purpose of that, in general is defined as meeting of our own needs without compromising the ability of future generations to meet their own needs. That's what the sustainability means. Sustainability can hold for different industries. We are more worried about construction sustainability. So that is able to maintain at a certain rate of level. So that same level you're going to meet. So you're going to use the material. What are the resources which are connected to construction? Not to excess use that, not to waste that. Pass on the resources to the next generation is what we call it as sustainability. So it's going to be rotating among the environment, economy as well as social. These three components are this we worried about. And so here we are worried about 2 points. One is how much energy is required to process the material, and then how much waste it's going to be generated. So in particular, industry is the one which we talk about. Here in specific, we are going to talk about construction. So construction sector makes a contribution to three objectives. Objectives we are going to talk in terms of a Venn circle, and then I'm going to explain about that using the different types of cycles of the structures and their projects. So these are all the things we need to before you go for environment impact, sustainable construction, design and management is also very important. So the three phenomena we talk about is environment, economical, and sustainability. So social impact. So we are going to talk about the whole cycle, how it's going to be starting its journey and how it's going to end, the materials which are related to the construction. So with due regards to the safety and then some ethics you need to follow, and it should all the technology which we are going to use should be eco-friendly. So that is the one more thing we are going to talk about. So actually, it won't be a fair choice to just focus on the development by compromising the resource and needs of the future generation. It is important to focus on the long-term goal and expansion without causing disturbance to the environment and utilizing the finite resource conservatively. So sustainable development is need of an hour. It's a very important topic to be covered and to be shared. It is a pressing priority to adopt sustainable approaches in the manufacturing of cement by cutting down the carbon emission. Carbon emission is one of the things which is given more importance nowadays. So, so if you are going to talk about the social impact of sustainable construction, we are going to talk about health and standards and ethics to be followed, not to be, it's all a combination, as I told you, social, economical, as well as the industry. So this, this the Venn diagram which shows the economic impact, environment impact, and social impact. Those three are the connection. So there's one which shows is shaded in all the three. This one, if you can see here, that one is common in of the three circle Venn diagram circles. So here we are going to talk about these three circles, subsets. We are going to talk about the three sets. We are going to talk about economic, environment, as well as social impact. So what are the positives? What are the negatives? Including all the three. Taking two at a time also, we are going to talk about that, right? So before we go for this, let me talk about this sustainability, the positive impact, that is convection. Considering all the three circles, we are going to consider the positive impact of the concrete. So let me tell that before you go for the, madam, am I audible? Madam, am I audible? And my slides are being shown. Slides are changing. Okay, thank you.
Yes, sir, you're audible, sir.
Thank you. Yeah. So first, let me define this embedded energy. The embedded energy is I think we are all aware of renewable and non-renewable energy resources. So non-renewable energy resources per unit of the building material is what we call as embedded energy, that is measured as megajoules per unit weight. Unit weight here is kg. So let's talk about the concrete. So different construction materials, we're going to talk about normal concrete, fired clay bricks, the road and pavements, glass, wood. Wood is of two types, multi-layered and the plain timber, and steel from the ore. Out of all these embedded energies, least for the normal concrete, and carbon emission is also least when compared to the other construction material available. So first of all, let me define what is embedded energies. The energy, the total energy required, summation of the energy required. So the energy required is while you extract in the mines, the ore you're going to extract from mine, that is the energy required, and then processing and manufacturing and transporting, distributing, assembling, and constructing. All these different energies are required at different point of time. You would add up all this, summation of all this is what we call it as embedded energy. So megajoules per unit weight. So as I told you, non-renewable energy per unit weight. Here you are taking that as concrete you are talking about. So here you have the least 0.95 megajoules per kg. And then the carbon emission is also least, that is kg per kg of carbon dioxide per kg of concrete. So 0.13. So you can make the comparisons here. So embedded energy is that from the extraction, processing, manufacturing, transporting, distributing, assembling, as well as construction. Different processes. Let me show you maybe in the subsequent slides what do you mean by life cycle assessment, and what are the different phases of energy consumption taking place, and how much carbon dioxide emission is also happening. So 2 points, this is very important when you talk about sustainability, is embedded energy required for whole completion of the process, starting to its ending. So until you put that in the use, and then how much carbon dioxide is emitted. So on that basis, we are going to define. So this is the positive impact of the concrete. So now we'll see the negative impact. Negative impact in the sense, actually, as I told you, it was prepared some 3-4 years back. So the data is pertaining to be 2020. So you can see here how the cement production is increasing year by year. You can see two colors. You can see one is low demand case, high demand case. So 2010 to projected up to 2015. So 2010 to 2015, you can see here it has, as of now, it is, 7 billion tons per year. You can see here somewhere, we are here somewhere between 20 to 25, you can see here. It is almost 7 billion tons per year. And when you go for the 2050, it's going to be 14. As I told you earlier, while introduction, I told you economy, infrastructure development, at any cost cannot be stopped. Only thing is we need to go for alternate materials. So whatever the technology, what are the developments happening in maybe in CSE or ECR, or mechanical, whatever that is, you definitely require infrastructure for their sustainability, right? So for that you require smart cities, you require a lot of roads, a lot of other construction development projects, and obviously you require concrete. So concrete, cement is the main ingredient of that. So we are concentrating more on cement in terms of sustainability. So as I told you, this all including of the three: economic, environment, social. Now we'll go for the two parts. So economic impact and environmental impact we are going to talk about. So each and everything we are going to talk about positive as well as a negative. See, a poor construction, negative impact we are talking about when we have the common factor between economic and environment. Poor construction, with concrete can lead to high repair and rehabilitation structure. So proper scheme of repair rehabilitation is required. If we don't give proper, somewhere else I was listening during some interaction or some workshop I was listening. Professor M.S. Shetty, I think all of you are aware of Professor M.S. Shetty is a father of concrete technologies. He is the author of concrete technology book also. He was telling, he was making comparison of a human to a concrete structure. During the early days, a small kid is born. You are going to how good feed you are going to give, that much resistance power he is going to have. Likewise, how much curing you do to a concrete in the early stage, that much strength and durability it's going to have in the later part of that, right? And then at the end of the death of the human, likewise the repair, right? Like after crossing 50, 60, obviously you have some type of disease. Likewise, the structure is getting old, you have some issues with that, some repair, rehabilitation has to come. So if you have good resistance, the end diseases will be less. Likewise, he was making comparison of a human to concrete, like how we exhale and inhale, like how we breathe. The same thing the concrete also has through these pores, fine pores. It's going to have this air going inside. So thereby, what happens is, as per his deliberation, he told is that you have some 5 to 10% of unhydrated grains inside the concrete. So once this exposure to air is happening, this unhydrated also gets hydrated. That's the reason you get the strength. So he has started comparing human to concrete right from birth to death, and how the resistance of early stage is going to help in the last stage of your life also, right? So why I talked all this is poor construction practices, right? If you are not paying more attention, quality wise, you are compromising at initial stage. Definitely high repair and rehabilitation costs will be there, and every year you need to spend more money for during this budget also, especially when you go for the constructions across the coastal line. Definitely you need to give attention to corrosion also. So those are the things you are going to. So you are going to cutting costs and compromising with the quality. Definitely your repair will be more. Rehabilitation costs also will shoot up. So I told you negative impact of this. Now we talk about positive impact of the concrete. So it's a long-term investment which is accessible, can be reachable for that, and proper material use, proper concrete being done there. Obviously, you'll have secure feeling. People living there, they will be having secure. So that is the one of the point to be discussed. The negative impact of this source sustainable of construction is that the concrete jungles. Now it's going to become concrete jungle nowadays. See, that's the reason, and especially when you talk about this Hyderabad, every time during rainy seasons they get waterlogged. Water percolation is not happening. Why? Because all the lakes were occupied, all the trees, the deforestation, everything. So more concrete jungles, more the concrete jungles, lesser the penetration, and obviously it's going to. So once you're going to play with the nature, nature will pay back with interest. That's what we have been seeing the past year. Now coming to this sustainability development. Yeah, sustainability development. They have got 17 goals. Now they are going to define 17 goals are there. I think maybe this visible to you or not. Let me tell this, but let me tell what are the 17 goals. The first one is no poverty. Right? Actually, the main aim of the sustainable development goal is to transfer the world to sustainability. Existing world to sustainable world is that the aim of. So 17 goals which they are defined is first one is no poverty, zero hunger is second one, zero hunger. Third one is good health and well-being. Fourth one is quality education. Fifth one is gender equality. Sixth one is clean water and sanitation. And seventh one is affordable and clean energy. Eighth one, decent work and economic growth. And ninth one is industry, innovation and infrastructure. 10th one is reducing inequalities. 11th one is sustainable cities and communities. And 12th one is responsible consumption and production. 13th one is climatic action. 14th one is life below water, ecosystems, how the ecosystem biodiversity is going to be affected. And 15, life on land. Of course, we also come under this. 16th one is peace, strong institution, justice to be done with no partiality. 17, partnership between the different people or for the end goal is to have sustainable construction, right? So this you can see in this figure people joining hands together for the conference of the parties to the United Nations Convention. The agreement was made to measure, report, and verify the emission cutting efforts, especially emission of carbon emission. So now the material footprint, carbon footprint is material footprint. That is total amount of raw material extracted to meet the final consumption is what in general material footprint. So amount of raw material extracted to meet the final consumption. So carbon footprint is also one which we are going to talk about. So these are all the some of the points to be considered here, sustainable practices to be followed, and then how to reduce the waste prevention. 3R: reduce, recycle, and reuse. And then how to use the fossil fuels and how to give subsidies to people who are rationalizing inefficient fossil fuel subsidies. All this you need to take into consideration. So now you can see here the cement production process happening. Actually, we see a cement bag, but the groundwork done to get the cement is a lot. That's what we are going to see how it's going to consume energy and how it's going to emit waste. Is the picture will show you clear, right? So you can see here CO2 output and energy demand. You can see here in this case. This red one is chemical process. This pink one is energy consumed, energy used for the CO2 output. So you can see a raw material preparation. So this during the cement production, you have raw material production, and process can be dry process or wet process, right? In the clinker production, where more energy is consumed, you can see 40% is energy, and during the chemical process, 50% we are going to use. For the grinder, it is 5%. CO2 output. Energy demands, you have fossil fuels, energy as well as electricity. So here 10% at raw material preparation and 10% at the clinker and 70% at the clinker production as well and 10% at the grinding, right? So as I told you earlier, almost 7%, 5 to 7% contribution of CO2 man-made activities, we are going to use that. So this more energy intensive stage out of all this clinker production is the most energy intensive stage. I think we have two stages. One is clinker stage, another is grinding stage. That I will be showing you. So you reduce the clinker, you are going to reduce the CO2 emission. So durability is also going to depend on what is the quality of the cement which you are going to use. So now you can see here cement productions It's the second largest production of the cement in the world after China, and it contributes to 5 to 7%. Right, these two figures shows you one is global, another one is local India. So different continent, different countries, how much they are consuming low demand case and high demand case. And the same thing in India also. This one earlier, I think we have seen. So now we are almost 7 billion tons, and it reaches to 14 to 15. So this is how the scenario, Indian scenario compared to the world production of cement. Now coming to the technology for the roadmap for the low carbon transition in cement, you can see here the more important point. The two graphs here shows you that that is the year here, and then what is the progress induction. So how much percentage progress indicator for using share of alternative fuels and raw materials, AFR we call that. So here you can see here it is 5%, and then it's going to be 19%, and at of 2014 it's going to be 24%. So you can show the different indicator, progression indicators. Alternate fuels is the first one. Second figure shows you the clinker to the cement ratio. So in general, the normal OPC after ordinary Portland cement have 95% of the clinker, 5% will be the gypsum. So these points you need to be taken into consideration. So energy efficiency waste heat recovery systems. So one of that is CCS, which I am talking about, carbon capture storage. This is the innovative technology nowadays. They're using carbon capture storage. So energy, improving energy efficiency, waste heat recovery systems, using alternate fuels and alternate raw materials. That is the one point which you have to stress more, using alternate raw materials, right? Instead of cement, what is the alternative material you're going to use? Instead of fine aggregate, what is the alternative material you're going to use? And instead of coarse aggregate, what is the raw material you're going to use? All this plays a more vital role. Now, reducing the clinker to cement ratio. So clinker is reduced, obviously carbon dioxide emission is also reduced. Earlier we have seen that. So clinker reduction, clinker can be replaced with some other materials. We'll be talking about that in terms of fly ash or GGBS or clay that we'll be talking about. So use of composite cements, I think if you can see yesterday our HOD sir, Professor Paparogar has shown some presentation of the composite cements about its properties and its stripping time also, advantages also he might have shown. So this use of these blended cements I'm talking about, LC3 also I'll be talking about later part of that. So CCS is the innovation technology which there is a carbon capture storage which makes make material recovery. Sometimes they store the carbon below the ground. Using the carbon waste, they make some materials. Recovery can be done. Otherwise, calcium looping will be done. Calcium looping, you call that as process. And combustion. These are some of the things which can minimize or capture the carbon storage process. So, as limestone is one which is maximum used as a raw material, the clinker, and others maybe the clay, marble, shale, red mud, all this will be there. So especially the four limestone rich belts in India, especially we have in Andhra Pradesh, four belts are there. Andhra Pradesh, Rajasthan, MP, Gujarat, Chhattisgarh, Tamil Nadu, and some parts of Telangana as well. We are going to have. So selection of the cement companies will also depend on the location of the limestone ridge. And electricity, we're going to produce 70% using as a coal, class C and class F that we'll be talking. So environmental impact will be can be controlled when you go for alternate source in the plant, right? So what happens is in cement plants, they are not going to depend much on the grid. They have their own dedicated coal burning, power generation grid on their own to produce electricity required for the coal burning in the thermal power station. So they don't depend on the grid. So the coal, as I told you, depends on class C or class F or the quality of the product which you are requiring. So gypsum can also be used as a phosphogypsum, which is a waste product from fertilizer industry. Instead of gypsum, you can use that. Otherwise, you can go for the alternate fuels like industrial waste and biomass or alternate fuels also you can use. So PPC cement, which has a cement pozzolanometer fly ash available to 20 to 40%, 25 to 35% has been given by the code. And it is a major, nowadays, most of the people are using Portland pozzolana cement. Slag cement also is now picking up. So 8% of the cement is being produced, and the substitution can be taken up to 70 to 80% in the slag, whereas up to 30 to 35% only in the class of in the case of a fly ash, as per the code. Now coming to the life cycle assessment, actually this is life cycle assessment is a hot topic going across the world, across the globe, and IIT Madras, a lot of research is being done on that. They compile and evaluate, take some inputs, outputs, and how it's going to impact on the environment product system is going to be. So it has got the 4 parts, that is goal and LCI, inventor analysis. So studies, analysis, assessment, and interpretation. So here in the first case, you are going to study what are the boundary conditions. Boundary conditions means that I'll be showing with the figures. Boundary condition is from the mine to the gate, and the gate to the gate. Gate to the gate is industry, and gate to the cradle, you call that. That is where mining is the cradle, you call that, and gate of the industry, gate of the end of the industry, and then to the grave recycling process. That I will be talking about later. So here it is going to define the boundaries, methodology, applications. The second one is a collection of data, inputs and output. And the third one is assessment of the analysis, how it's going to have the environmental impact, and recommendations will be done in the interpretation conclusions. So you can see here these applications of life cycle assessment. Applications of life cycle assessment is it's going to study the origin of the problems to any particular product or any process, and compare that to the given different products they are going to compare, and they go for the, using the given data, they go for the design of the new products, and a number of products are available, one which is better, evaluate, and then go for eco labeling or carbon tag. Carbon tag is nothing but it is an CO2 emission created as byproduct of manufacturing, transporting, and processing of a product. That's what I call it as a carbon tag. Byproduct of CO2 emission created as a byproduct of manufacturing, transporting, and disposing of a product. So now we can see here is LCI technique is used for assessing the environmental aspects and potential impacts associated with cement as well as concrete. Now we can see here there is a cement factory where you have energy fuels used and carbon dioxide emissions happening. So instead of fossil fuels, you can go for alternate fuels. Instead of limestone or clay, you can go for shale red bed. What would be the CO2 emission? What is the energy consumption? What would be the properties? All this will be studied. So this is what I was talking about, that is functional unit, cradle to grave. That is, cradle means where it has started its journey after mining, to grave means where it is unfit finally. That is what you call that as grave. So cradle to gate means from mining to cement factory in gate. Gate to gate means cement factory in gate to cement factory out gate. These are all the system boundaries you're going to use here. Now you can see here, this is the manufacturing of the material, different components, use that in construction of the material, and use and maintain. After that, after some years, some duration, you go for renovating, right? After that, transforming that, and if it's not still, you can go for dismantling. Otherwise, you go for reusing. So demolishing, burning of the term recycling. So this is the process which starts from the cradle. Cradle means a small baby when they are born, you put it in a cradle. That is what they mean by here, cradle, right? When the ore is taken out from the mines, mining after mining. So this one, earlier one, what I told was in general. Now we are talking about the concrete. So whole life cycle of the concrete and how it's going to have impact of the concrete from the cradle to grave. You can see here, this is the cradle, right? It's birth of the baby. That is the mining of the raw materials is being done in terms of cement, limestone. You mine limestone, right? Water, even aggregates. Also, I'll be showing off that in later slides. Aggregates and steel. So this all being done here, downloading with your mining of this. After that, you transport that to the cement factory and then do that cement processing, clinkering or calcination, whatever that is. Calcination, I'll be talking about that later. Clinkering is different, calcination is different. After cement manufacturing, you go for manufacturing of the concrete, placing in the site, use that and maintenance. After that, if you can reuse, that is fine. Otherwise, you demolish and dispose. That is the grave. So cradle, gate. Gate includes two gates. One is in gate and out gate. And finally, you go to the grave, death of the material. But this is starting of the material, birth of the material, death of the material. Instead, you can see here raw materials and how it's going to use and how the environmental loads are impacting on that, and what are the products and what are the byproducts, and how much energy is consumed. So you can see here, the pictures are very clear. You can see here. The first one is this is grave. Sorry, not grave. Cradle to gate. So this is the raw material extraction. This is the energy. This is the mine. So some energy or fuel is required to extract the ore or mineral from there. Extraction of the raw material. Some emission is created. In the first step, all emission is created. Next one, you transport the raw material to the cement plant. Here also, you are using some fuel for the transporting, but there also emission. Second part, emissions. So before you enter the cement factory, emissions are created at ore mining, and number two during the transport. And finally, you go to the cement factory, clinkerization will take place. Earlier, I told you using the kiln, you have this dry process, wet process. There you require fuel. So for mixing raw material, you require energy, and for the generation of heat also you require energy. So both fuel and energy are used for the emission process, creation of emission. And then after that is cement grinding or blending, whatever that is, you are going to grind that, and after that you are going to add gypsum, whatever that is. There also you require energy, and then packing of the cement also you require energy. So yeah, this is aggregate product. Earlier we talked about cement. Now this is aggregate. Aggregate also you have to mine that quarries, and you're going to use fuel. You have the emission as well, and then you need to crush them with the machine, and then you're going to crush that. You require energy as well, and transport that to the site. There also you require energy. Now we yeah, secondary cementous material, CMs you are going to use. So we are talking about coal here, and GGBS you are going to talk about. Rice and gas also we are going to talk about. So this is the fly ash for thermal power stations. So as I told earlier, 60 to 70% of the energy, electricity you are going to get from thermal power stations. So the raw material, that is the raw material uses coal, C class or F class, and end product or byproduct is fly ash, which consumes electricity and it releases carbon dioxide as well. Same thing with the GGBS also. In the steel plant, you're going to use this, you clinch that, slag, and water that, after that, dewater that, crush that, grind that, and you get GGBS, ground granulated blast furnace slag. For all these different stages, you require energy as well and they're going to produce some waste also. Likewise, this rice husk ash also, the controlled burning calcination is required. After that, you are going to use this rice husk ash, which is also secondary cementous material. So the impacts which can be calculated using different impact assessment methods available. This is all in general acidification, eutrophication, how it's going to deplete the oxygen, how it's going to affect the human toxicity, global warming potentials, as I told you, carbon footprint or CO2 equivalent emissions. As I told you, energy and carbon is the both things which are more concerned with the sustainability. So greenhouse gases, examples will be carbon dioxide, otherwise methane, nitrogen oxide, fluorine gases. These are some of the gases which are responsible for global warming. And this fuel energy consumed or emitted energy, which we already discussed earlier, right from mining to its manufacturing, fuel energy required, and raw material usage as well as cost. So this is boundary conditions. I told you earlier. This will clearly gives you some idea about how the cradle to gate to gate. As I told you, cradle to gate with where you are going to extract the raw materials using some energy. You can see the figures are very clear. You require some energy, extract, produce some carbon dioxide. Transport, use some fuel, produce some carbon dioxide. CSI is the Cement Sustainable Index, which will give a clear idea how much emission is happening, how much energy is being consumed. So this is gate to gate, as I told you, in gate to out gate. In gate is where the clinker is coming in, out gate is where the cement, which has packed cement, is going out of the gate to the godowns or silos, whatever it is, right? So this is the clinker formation, this is the energy required for the clinker formation, and cement manufacturing, you require some energy, cement grinding, in fact, as well as the cement packing also. You can very clearly see what is cradle to gate, gate to gate. So simple, we only see the cement bag, but all this story happens before the cement reaches to the counter, go down to our site. So this is the total ground to gate process involved very clearly. So what are the raw materials used there? How the grid from the grid, how the electricity is produced, how the water is used to limestone extraction in the quarries, and what are the different processes at different points of time, right? So if it is GGBS, how the grinding is taking place, fly ash, how it is calcinated clay. This is the LC3. We'll be talking about that later. So our main aim here is to study about SCM, fly ash, GGBS, and calcinated clay. This LC3 is the hot topic once again in IIT Madras. A lot of research is going across the globe, in particular Chennai IIT Madras. So you can see here it's of gypsum, phosphor gypsum you're going to use instead of some proportion of the concrete. You can use fly ash or GGBS and even clay also, which we are going to discuss. So boundary considerations which we have seen in the through the figure, all the process from the raw material mined to the gate of the cement plant, energy consumed at CO2 emissions. This has two, direct and indirect, are to be produced, right? Directly or indirectly, maybe bringing to the site and during process in the site also, we're going to have direct and indirect process, production of cement, and transportation also you require some fuel and alternative fuel, fly ash and gypsums are not are excluded in this boundary consideration. So this is inside the cement factory, gate to gate. So the raw materials, what are the direct raw materials, how the energy is consumed, what are the emissions and during the cement plant, which includes extraction, transportation inside the cement plant, and direct emissions due to fuels used in electric productions are also included. As I told you, we have dedicated electricity production in-house plant inside some of the cement factories. So CSI is the one earlier we have discussed, Cement Sustainability Initiative, which will define the boundaries also. It's a part of WBC. Yes, that World Business Council for Sustainable Development. So what are the emissions required, how much energy is consumed, and electricity also will be defined. So you have this absolute direct CO2 emissions, gross direct, net direct, which will include the electricity production and the biomass or fossil fuels, what are the case it is. And energy from fuels used in kiln and raw material dry issues are also considered. So we are going to talk about, we are going to see the process which is happening in a cement plant in India. That is the normal OPC cement, the PPC cement, PSC cement, and LC3 also we are going to see in fact. So you can see here the first one. These are all the raw materials which are required, right? Limestone, it all depends, clay or shale, water, bauxite, gypsum, or this performance enhancer. What is the performance enhancer? Means it's not the second generation additives added to improve the performance is what. See, actually the difference between additive and admixture. Additive is the chemicals which are added during cement production. Admixtures are the chemical admixtures added during concrete production. There is a difference. So here it is secondary generation which will improve the performance. Performance enhancers, you call that. Second generation of additives, you call it, right? So you can see here the major raw materials out of all this is limestone, coal, petcoke, lignites, and we are talking about inputs, that is electricity from the grid or fuels which you are using, the gypsum or clay, water, all this. So the main process would be like this: extraction and transportation of limestone, preparation of raw meal, thereof energy is required, preparation of clinker, preparation of cement, grinding, that is the grinding process, and then packing and dispatching. And you're going to have here is bulk cements or cement bracks or even clinker. So the earlier one which we have seen is OPC. This one is fly ash based PPC. So Portland pozzolana cement. Everything is similar to what we have seen earlier. Only new occupation is fly ash. Instead of excess limestone, you are going to use some of the fly ash here. So limestone, fly ash, coal, petcoke, lignite, all this, and other inputs are same: electricity, fuels, or gypsum, water, plant equipment. All these, the process also includes similar limestone extraction, raw meal preparation, and clinker preparation, and cement production, and packing, dispatching. Of course, here in the grinding stage, use the fly ash. Right, that is the addition one which you're going to. And of course, end products will be bulk cement, cement bracks, clinkers also. OPC is there, PPC is completed. Now coming to PSC. PSC is also similar to whatever you have done. Instead of the fly ash, you are going to use this as GGBS. So whatever the supplementary material you're going to use, you have to check the basic properties of that fineness. How much finer is that compared to the existing cement? All this. See, always remember while you go for the clinker. Am I audible, madam? My slides are moving. Hello. Yes. Okay. Thank you. Yeah. Yeah, at the clinker, no, the rate of cooling is also that the clinker rate of cooling is also very important. Grinding also is very important. Why? Because these two, rate of cooling and then grinding, also will play very important role when you go for when you go for the property studies. In fact, the strength and durability. The earlier days we are more worried about strength, but nowadays you require more of durability studies in par with strength, because a lot of issues are there with durability nowadays. A lot of pollution is happening. A lot of pollutions are happening, and you need to counter all these different chloride attacks or sulfate attacks, or especially the corrosion. The main corrosion is like a cancer in a human. You don't control the cancer cells in a human, it expands, it increases its territory. Likewise, you don't control corrosion in some part, it's going to increase, expand its territory. So the selection of the material, as I told you, GGBS properties and fineness is also very, very important. So of course, you know 33 grade, 43 grade, 53 grade, what is the fineness and what is the GGBS fineness, fly ash fineness, all will play important. So rate of cooling as well as fineness are also very, very important. So instead of fly ash, you are using here, yes. Yeah. Next, coming to this, still we are in life cycle assessment of the cement, impact assessment. We are talking about impact assessment. So you're going to conversions using some database and some data, some even some software also. They have done some, they have obtained some conversion factors for CO2 emissions as well as for the energy consumed, right? Energy consumed and energy, carbon dioxide emitted. So you can see here low priority to high priority. You can see here this Eco Invent 3D database, which is the life cycle inventory database. From there, you're going to get this IPCC. This one is Intergovernment Policy for Climatic Change. This is also data which you are going to get. EPA is US Environment Protection Agency, and of course, this CSA protocol, the Cement Sustainability Index protocol, which we have discussed earlier. And CHNS analyzer, which will analyze the carbon present, hydrogen present, nitrogen present, as well as sulfur present. All these, and can get the conversion factors. So these are the 4 steps before you interpret the results and draw the conclusions. Earlier I told you goal analysis, goal definition, and scope. You're going to define the scope. Sorry. And analyze the LCI, that is life cycle inventory analysis. That is, you collect the data from the cement factories, get the data on the aggregates, you have some inputs and outputs, and then you should go for the next assessment, will be done in the 3rd step. And so there, 3rd step, you're going to find these conversion factors using the data which we discussed earlier, and how it's going to impact on the carbon footprint and energy consumed. And finally, go for the interpretation where you draw the conclusions and give the recommendations, LCA, life cycle assessment for cement as well as for the concrete. Now we will be talking, so we have studied up to, we have studied life cycle assessment, and we have studied this supplementary cement materials up to now, and how it's being brought to the cement factory, how much energy is consumed, how much emissions is happening. Now we are going to have a case study. You're going to process. You're going to map some cement factories, and you're going to collect inventory collection material used there, and then you're going to have some analysis on this. So the 4 like some 6 cement factories. I think the slide. 6 cement factories were selected for the case studies. Ultratech, 2 Ultratech cement plants, 2 JSW cement plants, and JK Cement at 2. So this is the they have assumed that LC3 is assumed to be produced there. So integrated cement plant. Integrated means we know that where the clinker as well as grinding at a time they are going to take place. So it is Ultratech cement plant, Ariyalu in Tamil Nadu. They're assuming that to be done with OPC and TPC. And Ultratech cement says Arakonam, which is only grinding unit, right? Grinding unit means that the clinker is brought from some other plant and their grinding is being done. So OPC and TPC, they're going to use their produce there. So JSW, see here in JSW, nowadays JSW are completely replacing cement with GGBS. Lot of papers have gone through. Ultratech cement and of course JSW cement plant, they're using especially completely GGBS. They have done a lot of road work. They've done some shopping malls and even dams also they're doing, and a lot of information we are getting from them. So here also they're using, here you can see here OPC, PSC and GGBS. And second one, first one is at Nandyal, Telangana, Nandyal, Andhra Pradesh. and the second one is Thorangallu, Bellary, West Karnataka. There they are using PSC and GGBS. You can see the third and fourth they are using GGBS. So GGBS and Portland slag cement is different. GGBS, Portland slag cement, some portion of that they are going to use, but here it is complete. And the JK cement, Rajasthan is one of the limestone rich belt earlier we have discussed. So Nibaraha and Mangrove, Rajasthan, both integrated cement plants are going to have. So PPC and OPC cements they are manufactured. Now, this is the one which I was talking earlier, LC3, LC3, PPC, PSC, all of us are very familiar with just 1 minute. So LC3 is nothing but limestone calcinated clay cement, right? What happens here is only 50% clinker is there. The remaining 50% is replaced with three different materials. One is calcinated clay. Calcinated clay is waste clay in the quarries. So you don't need to go further for that. It is a readily available waste clay in quarries. And limestone means secondary limestone, unusable cement in the quarries. That also can be used. That is 15%. And 5% is the gypsum. So this is completely is what you call that limestone calcinated clay cement, LC3 call it, ternary blend. Earlier was binary blend, only two materials were used. Here it is three materials, clinker, calcinated clay and limestone. We call that as LC3, limestone calcinated clay cement. So a lot of research is being done here on this. Professor Ravinder Gettu, Professor Manu Santana, and Dr. Anil Shah research school, all these, they have done a lot of research on this. It's still going on in the research stage. So this is the clinker pictorial representation of LC3. You can see here, this is energy required to get the clinker and CO2 is emitted. So crushed stone, limestone, calcinated clay at 900 degrees Celsius, clinker, you grind that, you're going to get LC3. This is the figure which also shows you clearly. So LC3 earlier during figure only that is very clear, that is 50% is clinker, 30% calcinated clay, 15% is crushed limestone, and 5% is gypsum. So mass loss in clay during calcination is 13%. Some assumptions they have made here. Energy consumption for calcination of clay is taken as 2.6 mg per kg as reference, right? So electricity for calcination. So clinkerization is different from calcination. Clinkerization is the material manufactured during cement. Calcination is during clay heating. So another assumption is same fuel is used for clinkerization as well as for the calcination. And they assume that the transport of clay was done from Sarnapuri in Tamil Nadu. So this goal and the scope of studies. So you define goal here, analysis, assessment, and interpretation. The first one is the goal, that is to calculate the energy. From the last 1 hour, I was putting more stress on two parameters. One is energy, and number two is CO2 emission due to cement production. So that is the goal scope, right? So process integrated cement plant with dry process technology. Now not wet process, dry process technology. Unit is 1 ton of cement production. System boundaries is ground to gate. Ground is from the quarry to gate, cradle to gate, right? Next one, gate to gate, and third one is TSI. So these are the types of cements: OPC, PPC, PSC, and LC3. LC3 is just we have discussed. Next, analysis, second part. So this analysis data collection. So from the assessment studies, you can get what is that, how much is the composition of the raw material, how much is the position of the clinker. So they are collected a data for the assessment, and for the OPC, how much is being used, and PSC, what is the data, how much is being used, and how much is electricity produced, and what is the difference in terms of transportation, the difference in methodology, difference in process methods, all these things. Actually, it's a data collected from a cement factory. So earlier we have done the process map for OPC. We have seen process map for PSC. We have seen process map for PPC. Also we have seen. This is the one for the LCP production, a typical Indian cement. So here you can see the same thing. Earlier, whatever you have seen, limestone or oxide or clay. Here extra you have is the China clay, the clay which you are using. Calcination of the clay will be done here. So the remaining thing. This type of energies will be there. So the process includes same extraction, transportation, preparation of material, raw material, preparation of clinker, calcination of clay, preparation of cement, and here at this point you have add this limestone and clay, and then dispatching, and then packing and dispatching. Of course, cement, bulk cement and cement bags, clinkers you are going to use. This is a GIS tool prepared, like it will show the locations of the cement power plants, cement plant, clay mine, thermal power station, railway station. Why? Because accessibility of the material is also very important. So identification of clay and fly ash sources and transportation distances also is being calculated, and it will help us to identify the potential locations for LC3 plants. So GIS tool is to obtain the location of nearest clay mines and thermal power plants for transportation and the distance is also being calculated. This is prepared by Tara. Tara is it's a company. It's a Delhi-based company, which will give the sustainable solutions. Different methodologies, different products are there. They give the guidance, set of rules and regulations to be followed to get the sustainable. End of that, sustainable. So now the different materials inventory for 1 ton of clinker, if you can see here, this is taken, this is the example of, as I told you, some six cement factories, you have taken cement plants, you have taken, out of this is the Nandyal plant in Andhra Pradesh, where they have taken this for 1 ton of clinker, what are the raw material used, how much is fuel is required, how much electricity is produced on different heights. They have shown that, so limestone, 1420 kgs, like that, flue test, red mud, GBS, petcoke, fuels. What are the fuels you are going to use? Electricity. You are going to use that electricity for limestone crushing, raw mill, and the raw mill preparation, and coal, how much is this, and clinkerization, how much is this, and it's all this in kilowatt hour, and fuels are in kgs. Now the third one is selection of the conversion factors. So first one is the goal definition, defining of goal and scope. Second one is analysis of input data, and then conversion of this conversion factor is the third one. So life cycle impact assessment. After that only you have to go for the interpretation. So this is in line with what we have discussed earlier. Inventory results for the CO2 emission conversion factors, energy conversion factors from the low priority to high priority, the same one we have seen earlier, and which we already defined. Here it is for the life cycle inventory data base. Earlier was only for the OPC. So these are the conversion factors which you are going to use. This also they are going to use, get from the database and some software. They are going to use this, and they are going to get these conversion factors for energy required and CO2 emissions as well. So different heads, different fuels, how much is being taken, So truck values for the transportation, this location also is important. So ton per kilometer, all this is being calculated using the data. So this is the conversion factors you're going to get from this eco-invent database. Energy, this earlier one was direct, this one is indirect CO2 emission factors. So different energies, what are the raw materials, what is the fuel you're going to use, all this is being calculated. And finally, you go for life cycle interpretation, the last step in the life cycle assessment. So the pie chart is being prepared and to show the different energies consumed and how much of the CO2 is emitted per ton of the clinker is an example of a Nandyal integrated cement plant in Andhra Pradesh. So you can see that in the pie chart, you can clearly see here it is the maximum is being extracting and burning fossil fuels, and then limestone extraction, alternate fuels, the electricity transportation, and other subsidies, sundries will be there. And this is the first one. First pie chart is giving energy consumed. Second pie chart is giving the CO2 produced for the ton of a clinker. This is an integral cement plant at the Nandyal. And this life cycle assessment they are done for this CO2 and energy demand. So ground to gate to gate, and CSA. These all you see the values they get. So this is RLA or ground to ground CO2 emissions values and energy demand. So per ton of a clinker, and what are the values, specific heat consumptions, energy properties for fuel for clinkerization electricity. CSA values also they have found out. So now this is the comparison they're making ground to gate. So from the mine to the gate, clinker comparison they're going to make here and the different. So Ariyalur, Nandyala, Mangrove and Nimbera, these four they have made the conclusions, and they have found that this is between 850 to 970. That CO2 emission is they have done separately for the CO2 emission and separately for the energy consumed also. So it's between 850. The list is at Ariyalur, Tamil Nadu, and maximum it is 970 in Rajasthan. So this is how its CO2 emission per ton of the clinker is very equivalent. Kg CO2 equivalent to the ton of a clinker. So after clinker, you need to go for energy consumed. Earlier one was CO2 emission. This one is energy consumed, right? So here also you can see here the pie chart shows for the four different plants, and this energy consumed is showing between 4,500. Ariyalur it is minimum and maximum, and how the clinker you can see that clinker and clinker energy consumed and clinker CO2 produced are the same plants. You can see for the minimum and maximum values. So this is the energy consumed from ground to ground. This is GGBS. The earlier one we have seen OPC and LC3. This is for the GGBS. GGBS is exclusively, as I told you, JSW only. Exclusively, they are using this GGBS, right? So you can see here the values here. The energy is 93.939. You can see they show these charts, bar charts, and even for the CO2 emissions also they are shown the two different values. Both of them will hold good for the ground to gate. So it's exclusively for the GGBS at JSW. And this one will talk about calcinated clay. So the other four cement factories, of course, two cement factories where they're going to use this LC3 in terms of energy consumed, in terms of CO2 emissions happening. So there is not much CO2 emission difference. You can see here it was 247 and it is 248 kg per CO2 equivalent. And these two also you can see only 4% variation is there between the energy consumed. Now the materials used for 1 ton of cement. You can see here these all the values. The clinker, the first one is OPC, but clinker is 9-10 kgs, right? The remaining is limestone gypsum, and electricity transportation is common for all the 4 cases. And PPC is they are taking that as 30% fly ash. So PSC they are taking 15%. LC3 additional component here is the calcinated clay. You can observe here calcinated clay and limestone and gypsum. This is 500 kgs, 150 kgs, 50 kgs, and 300 kgs, and of course electricity and transportation. And so OPC, as I told you, 95% is clinker, 5% is gypsum, and so 48% slag, so 48 to 50%, whatever it is. So LC3 is calcinated clay from Dharmapuri, Tamil Nadu, from where they use that clay before beating. So now they made the comparisons of these CO2 emissions and energy consumed out of all these PPC, PSC, OPC, as well as LC3, both in terms of CO2 emission as well as energy consumed. Now you can see, you can read from this uh, graph, right? You can see the CO2 emission is 40% in PSC, you can see here. So LC3 it is only 33% and PPC it is only 23%, right, compared to the OPC. Likewise, reduction in energy consumed is PSC it is 24%, LC3 is 15%, and PPC it is 21%. So from C2 emissions, it is which one is better? Means PPC is better, and energy consumed it is LC3 is better compared to the OPC. So impact of LC3, you can see here they have done clays from different parts, and then energy consumed they have studied on this. This is the average they are taken as 2.6. So here 8% it's less and 5% is more. Emissions I'm talking about LC3. Energy also it is 12% more, 8% less. This is the reference they have taken. This 2.6 as the reference value. So now the goal here is to find out the energy required CO2 emission due to concrete production. So here you have taken the system boundary as ground to gate. So it is not RMC, it is on-site concrete production. 1 m cube of concrete you are going to take. And what is the use of this? You're going to get the sustainable indicators and to have this assessment, final assessment to draw the conclusion. So different SCMs are being taken here to study this. Some 30 samples were taken, and mix one. It is OPC. The first 4 are OPC. After that, the fly ash, 15% fly ash. C class 3 and F class 3, and then slag A and slag B, of course, 15%. And then we are going for 30% class C and F. So likewise, slag also 30%. And you can see here the M23 is a combination of fly ash as well as C class fly ash as well as F class. And 24 or 25 will give slag as well as fly ash, B and C. So last 28, 29, 30 will they have studied LC3 and different water cement ratios, and they have made the slump as 90 mm. So OPC and fly ash was obtained from Neyveli, Tamil Nadu, Sarvam Power Station, and slag from the Nandyala, Andhra Pradesh, and is calcitic clay from Gujarat. So these are some of the assumptions they have made here. Fly ash and gypsum are considered as waste products. Energy production using chemical is neglected, and the values, default CIMA Pro values, that is the values which you are going to get using the software, is from the drying, crushing, and grinding are considered. Cement is produced at Nandyala, Andhra Pradesh, and concrete is produced at Chennai. and all the data studies was being mixed design data studies was done at IIT Chennai, and clinker production, cement production process was modeled in SEMA Pro using the data. After that, we are going to get the values, and then comparison is being made. So this is the value LCA of the concrete process. Consider the complete picture tells you, the complete picture tells you about the process involved in production of concrete, right from the cement manufacturing. How do you extract the raw materials? How the coarse aggregate are extracted and then crushed, and then how the river sand is extracted, how it's mixed with water, how the slag is processed, and how the concrete is mixed, and the electricity, how it is used, how the fuse is extracted, and mixing plant, all this one will give very clear cut idea about all this. Complete process. So this is the one which will give there are 30 samples, the 30 samples which we have studied, energy consumed of the concrete and CO2 emission. So from here you can see here, decrease in clinker content reduces total emission. So 35 to 45%. That is what sustainability. So 35 to 45% is reduced. When you reduce the clinker and replace that with some sustainable materials, energy consumed is also reduced. So energy consumption, so double benefit you are going to get. So energy is consumed is less, waste production also is also less. So these all will maybe I don't know. This is it clear or not? Okay. So, so the conclusions finally, when I go for the conclusions, you can see here inventory data you have collected for the conclusions. You have collected the data, right? So the data tells you that energy consumed and the CO2 emissions are being done. So life cycle assessment is done to estimate CO2 emissions and energy. So choice can be made on the conversion factors, and the case to be considered for the cases which you have discussed, right? C2 emissions, and then in terms of the energy consumed, you can see here, blended cements have much lower CO2 emissions than OPC, with the LC3 giving the best. So energy consumed is PPC is best. Earlier I told you with some percentage variations also I told. So the bottom line is blended cements binders reduces the environmental impact significantly. So what happens is the cement industry being a contributor to greenhouse gases and carbon emission, there is a pressing priority to work on the reduction of carbon footprints to ensure sustainable development. In addition to the reduction of the carbon emissions, reducing clinker to cement ratio, that's what by the replacement, and using blended cement will improve the quality and long-term performance of concrete. Improvement of concrete performance and structural durability leads to less repair work and renovation, new construction, which will save cements and construction materials as well. This CCS is carbon capture methods also you can use. And for the further optimization, innovations also can be studied. Unwanted pollution materials generated during the cement manufacturing process or from other industry can be recycled or reproduced, right? So adopting circular economy by organization is important to achieve sustainable development and make this earth as green as possible. So to live us safely, to breathe safely, we need to have greener place. Adopting the approach shall immensely help in reducing wastage and landfill dump, which also help making earth a clean place to live. So these are all some of the points I need to. So sustainable development is the need of the hour, and I really congratulate the KL University authorities, Department of Civil Engineering, for taking up this particular theme as the FTP. So any queries? I'll stop the presentation here. Any queries? Need to answer.
Hello everyone. If you have any doubts, you can feel free to ask. Please share your queries in the chat box.
The screen is not changing again. Thank you for your kind words. Sure, sure. I'll share the PPT definitely. Sure, sir. I'll share.
Sir, I guess there are no questions for anyone.
Okay.
We'll wind up the session here.
Okay, madam. Okay. Thank you. Thank you, sir. Thank you. Once again, I'll thank you, the Department of Civil Engineering, Care University, for giving me the opportunity to showcase my.
Sir, there is a question, sir.
Okay.
Regarding GGBS, I heard Tata Steel has also commercial sale. Is it tested by you?
Yeah, yeah. Let me see the question. Yeah, yeah. Regarding GGBS, yeah, Tata Steel has also commercial sales that's happening, but that is not the material which I have tested. But a lot of research is going on in that point. In this direction, a lot of research is going.
Thank you, sir, for your wonderful session. Your
Thank you.
detailed analysis of the sustainable parameters in concrete system with practical examples has truly enlightened us today. So on behalf of everyone here, once again, thank you, sir, for the time and effort you dedicated in preparing the presentation. We look forward to implement the knowledge we have gained today.
Thank you, madam. Thank you. Thank you very much.
So you may leave, sir.
Okay, madam. Thank you.
Thank you, sir. And I request all the participants to fill the feedback form given in chat box.